Oscar Angulo, I believe. Following on the same theme, modeling oosator performance. Okay, thank you very much.
Right. Good afternoon, everybody, ladies and gentlemen. I'm glad Mr. has this introduced because is my work is very linked with one of the stages before stages of that we are talking about the delivering drugs. The title of my work is Modeling Oosator Performance. It's a case study of solving a problem in dense granular flows. This is no University of Loughborough, it's University of Greenwich, don't take it bad. My name is Oscar Angulo, as you said. I'm a PhD student at the Wolfson Center for Bulk Solids Handling Technology at the University of Greenwich. It's a project sponsored by GSK, and it's a work between Professor Bradley, who is the director of the center, and Dr. Berry, who is speaking. To start, an overview of what I'm going to talk, which is what is oosator, what is oosator principle, objective of the project, modeling of the oosator, characterization of powder, and I'm not going to talk about many of the characterization of powder. I'm going to talk just about just three of them, which is wall cohesion and adhesion, bulk density and compaction curve, stress ratio K and K meter, validation of the model with a test rig, and then a conclusion. To start talking about oosator, what is oosator? Well, we are talking now in pharmaceutical field. We are talking about one of the system of filling system for capsules, tablets, in more specific for dry powder inhale, which is delivered sometimes by tablets, small tablets, and then with the blister you break up the lamp and then you inhale the powder, or maybe as the Novartis used the system. Have you ever played when you were a kid with the straw, with the soft drink, with the Coke, trying to take some amount of the Coke? This could be one of the sample of oosator, trying to get one dose of the liquid, or even when you take a sample in the laboratory as well. Or think about the piston when you just push some liquid or whatever it is. So we are talking now, this is the oosator, which is have a body of the oosator, and inside has a pin, yeah? So in this cavity here, you get the dose that you're gonna put, for example, in the inhale or in the tablets for the others function. What is the objective of the project? Is to do a mathematical model to predict what happened in the process inside the oosator, how to get the dose, to get accuracy in the dose. But as well, sorry. As well, we need to talk about flow properties, because the model works with the flow properties. It depends how behave each powder with the many characteristics, as you say, with the air, how behave friction, compaction, and so on. Predict the model, how it works with one powder to another powder with all the characterization information that we get from the bulk solid characterization. And then verify the model using a test rig that we built up at the center. Now, let's talk about oosator principle. This is how you get the dose to delivery. We go here to the oosator, and we have a trough or bowl or whatever you want to call it, and we have full of powder. The oosator comes down and get some material inside. That's the incoming stage or filling stage. Then some powders require that you need a compaction here from the pin, but some of the powders doesn't need it because it depends on the properties of the material. And then the dosator is ready to do the ejection, so you go right here at the dose, and then it's ready for the ejection. But sometimes you need a previous stage before the ejection, which is sometimes you get extra material that you don't need or you don't want, and it's gonna make bigger dose, and maybe it's not good for the health of the customers. So it's coming a doctoring stage where you remove the material that you don't need, and then you just do ejection force with the pin inside. Right, so what are the factors involved in the project? So we got here a picture of the dosator in a powder bed, and then it's involved the bulk solid characterization, how behave the powder. The wall friction is very important. What is the friction between the material and the wall of the dosator, or even the face of the bottom face of the pin, where it's going to be the ejection, because it could be stuck the dose over there and it's not going to do ejection. Bulk solid bed condition, very important. If it's, you get, for example, segregation here, and then when you get delivery, you get the dose, so maybe you get all fine particles, or just coarse particles, or big particles, or lumps, or whatever. So it's very important. Or if it's any air pockets or lumps at the moment you do the stroke and pick out the material, so it's not, you're not going to get a good dose. Forces in the process, all the forces that happen in here, what I'm looking for, and the mathematical model is just what is happening here inside. The process speed, penetration of the dosator, how close come the dosator here. We observe that in this case, just go to the end of the trough. There is no any clearance here. So we found now there is a big influence problem with that distance in terms of the forces. The permeability, fluidization, what happened with air, how behave the powder with air in the moment where it start coming down and pick out the material. The pin force, what is the minimum pin force that you require to eject the dose? And everything is going to get improve the pin design and even the body design, and also to get accuracy on the dose, which is very important, because there is some facts as well. For example, for the company of Mr. Philip, is how strong you need that dose is for the people who use the blister to break up the lump, or even when you fill up the tube that you use in the inhale, how compaction should be that dose to get to come through your lungs. So, talking about modeling of the dosator, we use the Janssen effect applied in dosators, where we have the dosator inside the powder bed. If you check here in the powder bed, we have a graph here with pressure distribution against depth, the depth in here. So if you check the bulk solid bed outside, it's going to behave as a liquid. It's not any changing. It's not changing the bulk density. But also, but what is happening here is we go a curve like that, and why this shape and not with exponential shape like that is because the forces inside. So this is a big challenge to understand what's happening here, and it's a big challenge in the pharmaceutical industry to know what's happening, how behave the powder, what do you have, what you're selling to people. This point is very important. We will see later on where those curves intercept. We use as well, it's called the method of differential slices. So we divide this, as you notice in this picture, we divide by slices the bed powder and also the powder inside the dosator. And then if you take one of the slices, you have one slice with diameter D and the height dz. And then you have a vertical stress here, which is from the previous slice, could be, you have a vertical stress from the self weight as well, and you have and contribution of the shear stress, which is coming from the friction. This force here is giving us the shape that I showed you before, the exponential shape in the previous slide. You think you have a piston, you're pushing the powder inside the dosator. And then you have a resultant here, which is going to be transmitted to the next slice. And then you have a horizontal stress here inside the dosator from the vertical stresses. And then you have a vertical horizontal stress from outside, from the bed of the powder. And as you notice here, we have a stress ratio K, and here is multiplying and here is divided, but it depends on the state of the powder in the moment, if it's passive or if it's active. But it's a very important value because it tells you how behaves the powder, how it's going to respond to the vertical stress applied. So this is how it looks roughly. I haven't finished the model. This is how it looks roughly. You have here, you put some parameters of dimensions, diameter of the dosator, and then you take some characteristics from the bulk solid characterization as friction, angle is a friction, angle of the wall friction, internal friction, and so many. That's, if you see this graph here, we have horizontal stress in PAs in this axis and length of the dosator in this axis. So it's the same graph I showed you before when I was talking about the pressure distribution. So again, you see here how behave the bed, behave as a liquid, constant. But inside the dosator, it behaves like that or even like that. The difference between this blue curve is because one is what I assume some values at the beginning before I start doing iterations. And in this point is telling me how much material I can allow inside the dosator. Yeah? But when you check what happened with the bulk density, and you do some corrections, and then you put what is happened with the permeability, what happened with the air, and all the information that you get from the characterization, you maybe get here or even more down. So it's quite interesting, and some values that you can get in the model. Some here calculations for the dosator and then for the bed. I'm not gonna go in detail, but it's just this one is not gonna work if we don't do any characterization of the powder. So we maybe get wrong values. So let's talk about characterization of powder. I'm not going to talk angle of repose or something like that. I'm just going to talk from some of the main ones. I'm not going to talk about fluidization because I don't have time to talk about it, but let's talk about wall cohesion and adhesion. It's very important to understand the cohesion of the powder, because maybe is the cohesion that is involved in the dose, that keeps the dose inside the dosator. In the moment when the dosator comes up, ready for, after the stroke, ready for dejection, if it's not any friction between the material and the wall of the dosator, or the properties of the cohesion properties of the material, the dose is gonna just come down, it's slip down, it's not even lifted, and it's gonna come empty dosator. So to know how behave the powder with that material, with the material of the dosator, is very important. So we have here a graph. We have in this axis wall cohesion in kPAs and some wall surfaces, as you can see here, in different level of pressure, and you see it behaves totally different in many of them. So it depends on the material, it depends on the powder, how they together interact. Let's talk about bulk density and compaction curve. Bulk density is the headache for everyone to know how behaves the powder. So we bring the material to level of compaction, and then we can see how change the bulk density, how change the volume as well. So you get a curve like that, with a curve like that, you have this equation and you can put inside the model and you can roughly predict how it's going to behave the powder and how it changes the bulk density. So if at the beginning I assume I have a slice with a height of 1 millimeter, after you see how it's changing the bulk density, you'll notice it's going to be 0.7 millimeters each slice in average, and it's different the weight and so on. Let's talk about K and K meter. So again, it's a relation when you apply vertical stress and you get horizontal stress. We have something that is called K meter to try to get that value. So we have a cylindrical ring, you can call it like that, and then you cut it in half, as you see here and here, and then you have two load cells here, and then we apply a vertical force here, and then we sense the horizontal stresses in this direction with the load cells. Why too? Just for the stability of the system, and then to get better results. This is some results from the K meter. We're still improving because we need to reduce some friction issues, but it's roughly what you can get. So we have in this axis horizontal force in kilograms, and we have time here. So we can see here some stage. As soon as it's a slope here, and when you're doing the filling stage, when you're filling up the cylinder, and then you get this, what is the horizontal forces from the self-weight, and then we start applying some forces here, and we get the peaks with the horizontal force response. But what is as well very important, as soon as you take out, when you take the stress, when you're not applying loads anymore, there is some retaining stresses here, as you can notice here and here and here, and increasing here. That maybe is going to give information out, is going to give us an information on how much material could be handled inside the dosator, and is not going to slip down or could be things. So this is a graph from the previous slide. So we have here horizontal stresses in kPas against vertical stresses in kPas. This line here will give us that value of K, which is about 0.34. It could be between 0.35, 0.6, depends on the material. And this line here is the retained stress that we observe as well. So in this zone could be the key of the information of how much material is going to be in the dosator, how much is going to be retaining here. Now, we had to build up a test rig to validate the model to see if what we're calculating is roughly in what is happening in the reality. So this is a sketch of the test rig that we built up, where, as I showed you in the preliminary slides, there is in the reality the dosator comes down and pick up the material and then come back. In this case of the test rig, what is going to be fixed is the dosator, which have here the body of the dosator and here the pin. It's going to be fixed, and we are going to bring the powder up to sense what are the forces here, what are the forces, the ejection force of the pin, and also the forces from the powder against the body of the dosator. So we have here a trough, a cross section. We have a powder filled out with powder, and then the dosator body is fixed in a balance beam. We have a pivot point here and a counterweight here to offset the weight. And then we have a load cell here to sense the forces in the pin, and then a load cell here to send the forces against the body. And then we have a position transducer to know the position of the pin, and another one here to know the position of the trough. So, and then hydraulic system to give a movement, and then lab you to process, to control the rig. So how it works, it comes up, and then in this point where it's touching the powder is touching the body, is sensing here, and sometimes is sensing here as well as soon as it's filled full of the material. And then if the powder required, you do a pre-compaction, but it's not happening all the time. And then the trough comes back, and then we have it's a rotation movement, and then we are ready for the ejection. So we just do ejection and see what is the weight of the dose. So there's some results from the test rig. We're still doing some improvement. This is how it looks, roughly, the rig. And but what is important here, this is the bottom of the trough, and then here is the body of the dosator. So we can adjust the height of the pin, so get different geometry of the dose, more high or more smaller doses. Get different separation between the bottom of the trough and the pin, which is in this practical test rig we found now this very, very important. How much is this clearance in terms of the forces, and also what is the condition of the bed of the powder is very important, and there is not many studies in depth about what is the bed condition of the bed, because we get sometimes you get air pockets inside, you get lumps, we get different value fees if we don't pre-condition the bed of the powder. If we leave it, just break the lumps and fill up the trough, or you just get some level of compaction to get better dose. So here are some examples, data from the test. So we have in this graph two y-axes, one for the forces from the body of the dosator and the pin, and one from the displacement of the trough and the pin, and is against the time. So we have here the filling stage, where you can see in the purple color where is the displacement of the trough. So the trough comes up, and in this point roughly touch the material, and then we start sensing and get some values for the forces from the powder against the dosator, the body of the dosator, and then as soon as full the cavity, we get some forces against the pin in here, and then as soon as we put it down the trough, exactly in the same time disappear all the all right. And then here the ejection force, we have here what is the ejection force, the pin force, and then here we go mirror effect from the body of the dosator. We have here just repeatable test, and just for the pin force, so the force against time, and here for the body force. So you can see the filling stage and ejection stage, and you can see it's quite repeatable, and the mirror effect. Something important, we get as well dose weight. We have in this axis weight and in this axis test. So the blue ones are for different clearance. It's quite close, the clearance between the dosator and the bottom of the trough. And also here is a quite big gap. Here is 0.3 millimeters and here is 2 millimeters. So we get different weight of the dose here. And also the dark colors is when the beds are pre-compacted. So 2 kilos pre-compacted and no compaction of the bed. So we get different results. And so how much you need to be pre-compacted bed to get a really, really good dose, and the dose that the people need to break up the lumps, get the powder, and then inhale it. Some conclusions: the model will provide a useful tool to get accuracy in the doses, but also to upgrade the design of the dosators, everything based on the bulk properties of the powder, and also we improve insight into the effects of the following variables under laboratory control conditions as blend formulation, different bulk characteristic, dosator speed and location, material construction, ejection force. But another factor, potentially significant influence of the dosator process, which has not been studied in depth, as I said before, is the condition of the bed. Maybe it's one of the key as well for the problems that Philip mentioned before. And also the test rig, the model will be adapted for the future trends in powder fillings. So thank you very much. Any questions?
probably just one question of it. Bob?
When you do your K-meter test,
Yep.
do you get a Janssen effect? So you get a quantifiable difference between what you measure for the top and the bottom, which then is not a random error, but is a systematic error?
With the DK meter, we haven't got any like totally a Johnson effect because we try to minimize the friction on the walls. So what I put was I put a latex around the walls and put some lubricant, so I minimize. So I'm still reducing more just to get the pure relation between the stresses.